Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The vast cosmos stretches out before us, filled with wonders we've only begun to understand. From the swirling galaxies that populate our observable universe to the fundamental particles that make up all matter, science has revealed an astounding reality far stranger than fiction. Yet perhaps nothing captures our imagination quite like the concept of wormholes, theoretical tunnels through space-time that might connect distant regions of our universe or potentially even separate universes altogether. As we gaze outward with our most sophisticated telescopes, we observe a cosmos limited by the speed of light and the expansion of space itself. The nearest star system, Alpha Centauri, lies over 4 light-years away, meaning light itself takes more than 4 years to reach us. The distances to other galaxies span millions or even billions of light-years. Human exploration at conventional speeds would require timeframes that stretch beyond the practical lifespan of our species, let alone individual explorers. But what if there existed shortcuts through the fabric of reality? This is where wormholes enter our scientific discussion. First conceptualized mathematically in 1916 by Ludwig Flamm, while examining solutions to Einstein's field equations, these theoretical tunnels later gained prominence through the work of physicists Albert Einstein and Nathan Rosen in 1935. Their Einstein-Rosen bridges represented the first mathematical description of what we now commonly call wormholes. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. Unlike the science fiction depictions we've grown accustomed to, real wormholes arise from genuine solutions to Einstein's equations of general relativity. These equations describe how mass and energy curve the very fabric of space-time. Under specific mathematical conditions, this curvature can theoretically create tunnels connecting distant points in space and time, or potentially even different universes within a larger multiverse structure. The term wormhole itself wasn't coined until 1957, when physicist John Wheeler used the analogy of a worm tunneling through an apple as a shortcut between points on its surface. This vivid imagery helped scientists and lay people alike conceptualize these complex 4-dimensional structures within the framework of our 3-dimensional understanding. Today, wormholes remain purely theoretical. No observational evidence has confirmed their existence, yet nothing in our current understanding of physics explicitly forbids them either. This tantalizing possibility leads us to profound questions. Could advanced civilizations, or perhaps our own distant descendants, harness these cosmic shortcuts? And if so, might they lead not just to distant regions of our universe, but to entirely different universes altogether? To properly explore these questions, we must first understand what modern physics tells us about the multiverse hypothesis, the theoretical nature of wormholes, and the extreme challenges involved in creating or stabilizing such structures. We must examine both the promising mathematical frameworks and the seemingly insurmountable physical obstacles that currently stand between us and wormhole travel. The journey through this cosmic possibility begins with understanding what wormholes actually are, not as depicted in Hollywood, but as they exist in the equations of our most advanced physical theories. Only then can we assess whether they might someday serve as gateways to worlds beyond our own. To understand wormholes scientifically, we must first recognize their mathematical origins in Einstein's general relativity, a theory that reimagines gravity not as a force, but as the curvature of space-time itself. When massive objects like stars and planets warp the fabric of space-time, this curvature dictates how other objects move. This revolutionary concept transformed our understanding of the cosmos, explaining phenomena from the precise orbit of Mercury to the gravitational lensing of distant galaxies. Within this mathematical framework, certain solutions describe tunnels through space-time. The simplest such solution, the Schwarzschild wormhole derived from the Einstein-Rosen bridge concept, connects 2 separate regions of space-time through a throat or tunnel. However, this basic wormhole model presents immediate problems. Calculations show it would collapse instantly, making it traversable neither by matter nor by light. The fundamental obstacle to creating stable, traversable wormholes lies in the very nature of gravity itself. Under normal circumstances with ordinary matter, gravity always attracts. This attractive force causes the throat of any naturally occurring wormhole to pinch off immediately after formation, severing any potential connection between the regions. It briefly joined. To counteract this collapse, a wormhole would require what physicists call exotic matter, theoretical material with negative energy density. Unlike all known forms of matter and energy in our universe, exotic matter would generate repulsive gravity, potentially holding the wormhole's throat open against its natural tendency to collapse. Quantum field theory tentatively suggests such negative energy states might exist in limited contexts, such as the Casimir effect, where quantum fluctuations between closely spaced conducting plates can create small regions of negative energy density. However, the quantities required to stabilize a macroscopic wormhole would be immense. Physicist Kip Thorne and his colleagues at the California Institute of Technology calculated in 1988 that stabilizing even a microscopic wormhole would require negative energy equivalent to the mass energy of Jupiter, but with the opposite sign. Creating, harnessing, and deploying such exotic matter remains far beyond our current technological capabilities, perhaps even beyond what the laws of physics will ultimately allow. The challenges compound further when we consider the immense tidal forces present near the throat of a wormhole. Similar to the spaghettification effect near black holes, these forces would likely tear apart any physical object attempting passage. Some theoretical models suggest these forces could potentially be engineered to remain survivable, but this would require even more precise manipulation of exotic matter. Temperature presents another formidable barrier. Calculations indicate that the throat region of a traversable wormhole would likely experience extreme temperatures, potentially approaching the Planck temperature of approximately 1.4 times 10 to the 32nd power Kelvin. For comparison, the core of our Sun reaches only about 15 million Kelvin. No known material could withstand such conditions. Additionally, wormholes might be subject to dangerous feedback loops. Theoretical work by physicists, including Hawking, suggests that quantum fluctuations near the event horizon of a wormhole could trigger exponentially growing oscillations that would destroy the wormhole almost instantaneously after creation. Despite these seemingly insurmountable challenges, theoretical physics doesn't explicitly forbid traversable wormholes. Rather, it suggests they would require physical conditions and technological capabilities far beyond our current reach. The equations themselves remain mathematically consistent, leaving open the tantalizing possibility that advanced civilizations might someday overcome these obstacles through technologies we cannot yet imagine. The concept of a multiverse, the hypothesis that our universe is just one among many, has transitioned from fringe speculation to mainstream theoretical physics over recent decades. Unlike science fiction portrayals of parallel worlds where slight variations create alternate histories, scientific multiverse theories emerge naturally from established physical frameworks and attempt to explain observed phenomena. Several distinct multiverse concepts exist within modern physics. The most conservative arises from inflationary cosmology, developed in the 1980s by physicists including Alan Guth and André Linde. This theory explains why our observable universe appears flat, homogeneous, and isotropic by proposing a period of exponential expansion in the universe's first fractions of a second. Importantly, eternal inflation models suggest this process continues indefinitely in other regions, spawning separate bubble universes with potentially different physical properties. String theory, our leading theoretical framework for unifying quantum mechanics and general relativity, suggests another form of multiverse. When extended to M theory, it requires extra spatial dimensions beyond the three we experience daily. Different compactification patterns of these extra dimensions could yield an estimated 10 to the 500th power, different possible universes, each with distinct physical laws, dimensional properties, and fundamental constants. The many worlds. interpretation of quantum mechanics, proposed by Hugh Everett in 1957, offers perhaps the most radical multiverse concept. This interpretation suggests that quantum events don't resolve to single outcomes, but instead cause reality, to branch into different worlds containing each possible outcome. If correct, this would mean new universes are continuously forming at every quantum juncture, an effectively infinite multiverse of quantum possibilities. Cosmological natural selection, proposed by physicist Lee Smolin, suggests universes might reproduce through black holes, with slight mutations in physical constants. This evolutionary process would naturally select for universes that maximize black hole production, potentially explaining why our universe seems fine-tuned for complexity. Observational evidence for any multiverse theory remains elusive. Critics argue that multiverse theories may exceed the boundaries of empirical science, since other universes, by definition, lie beyond our observable reality. However, proponents respond that indirect evidence might still be detectable, such as signatures of collisions between bubble universes imprinted on the cosmic microwave background radiation, or statistical patterns in physical constants that suggest selection effects. Recent observations from the Planck satellite and other cosmic microwave background experiments have placed constraints on certain multiverse models, but haven't definitively confirmed or refuted the broader concept. Some theorists, including Max Tegmark from MIT, argue that the mathematical consistency and simplicity of multiverse theories provide theoretical support even absent direct observation. If multiple universes do exist, connections between them would represent the ultimate frontiers of exploration. Wormholes potentially connecting different universes, referred to as inter-universal wormholes in theoretical literature, would operate under principles similar to intra-universal wormholes, but with added complexities. Different universes might operate under different fundamental physical laws, raising questions about the stability of any connection between them and whether transit would even be physically possible. The cosmic censorship hypothesis proposed by Roger Penrose suggests nature might forbid naked singularities, points where space-time curvature becomes infinite without being hidden behind an event horizon. Some physicists extend this principle to suggest that stable connections between fundamentally different universes might similarly be prohibited to maintain causal consistency. However, these remain open questions at the frontiers of theoretical physics. A revolutionary development in theoretical physics has emerged over the past decade, linking two seemingly disparate concepts: quantum entanglement and wormholes. This connection, known as the ER-EPR correspondence, Einstein-Rosen bridges, Einstein-Podolsky-Rosen entanglement, was proposed in 2013 by physicists Juan Maldacena and Leonard Susskind. Their work suggests that quantum entanglement and wormhole geometries may be fundamentally the same phenomenon, viewed through different theoretical frameworks. Quantum entanglement occurs when particles become correlated, such that the quantum state of each particle cannot be described independently of the others, regardless of the distance separating them. When measurements are performed on entangled particles, the results show correlations that cannot be explained by classical physics. Einstein famously referred to this as spooky action at a distance, considering it a potential flaw in quantum theory rather than a genuine physical phenomenon. Yet decades of experiments have confirmed entanglement's reality. The most sophisticated tests, including those performed by physicist Anton Zeilinger's group, have shown correlations between entangled particles separated by more than 1,000 kilometers. These correlations appear instantaneous, seemingly violating Einstein's cosmic speed limit, the speed of light. The ER-EPR correspondence provides a compelling resolution to this apparent paradox. It suggests that entangled particles are connected through microscopic wormholes, quantum tunnels through spacetime that create shortcuts between the particles. Under this framework, the spooky action isn't traveling through normal space, but through the wormhole connection, maintaining relativistic causality. This theoretical breakthrough emerges from advances in understanding quantum gravity, particularly through the anti-de Sitter conformal field theory, AD-CFT correspondence, developed by Maldacena in 1997. This mathematical relationship demonstrates how gravitational systems in a space with negative curvature, anti-de Sitter space, can be exactly equivalent to quantum systems without gravity operating on the boundary of that space. Through this correspondence, quantum entanglement in the boundary theory translates to geometric connections, wormholes, in the gravitational description. While these quantum wormholes bear little resemblance to the macroscopic tunnels of science fiction, they suggest a deep connection between quantum information and space-time geometry that might someday be exploited for technological purposes. Recent quantum simulation experiments have begun testing aspects of this correspondence. In 2019, researchers at Google's quantum computing laboratory demonstrated a traversable wormhole protocol in a quantum system, showing how quantum information could appear to travel through a simulated wormhole created through quantum entanglement manipulation. While not creating actual space-time wormholes, these experiments probed the theoretical connections between quantum information and space-time geometry. If the ER-EPR correspondence proves correct, it suggests several profound implications. First, the fabric of space-time itself may emerge from patterns of quantum entanglement between fundamental constituents of reality. Second, manipulating quantum entanglement might theoretically allow for the engineering of space-time connections. 4. Multiverse exploration. This connection offers intriguing possibilities. If separate universes within a multiverse retain quantum correlations from common origins or through quantum fluctuations at their boundaries, these correlations might correspond to traversable wormhole connections under the right conditions. Theoretically, advanced civilizations might exploit these natural quantum connections to establish more substantial inter-universal links. However, significant theoretical and practical challenges remain. Current quantum technologies can only maintain entanglement between small numbers of particles in carefully controlled laboratory conditions. Scaling to macroscopic wormholes would require quantum coherence across billions of particles, far beyond current capabilities and potentially physically impossible due to decoherence effects. If traversable wormholes could theoretically exist, what technologies would be necessary to create, stabilize, and navigate them? Current scientific understanding suggests technological requirements so far beyond our present capabilities that they appear effectively impossible. Yet history repeatedly demonstrates how yesterday's impossibilities become tomorrow's routine achievements. The first technological hurdle involves exotic matter production. As previously discussed, traversable wormholes require material with negative energy density to prevent gravitational collapse. While quantum field theory allows for small-scale negative energy densities through phenomena like the Casimir effect, engineering materials with persistent large-scale negative energy remains beyond our theoretical understanding, let alone our practical capabilities. Some theoretical approaches suggest alternatives to conventional exotic matter. In 2017, physicist Pascal Coiron published calculations suggesting that certain configurations of wormholes might remain stable with significantly less negative energy than previously thought. Other approaches explore whether quantum effects near wormhole mouths might naturally generate the necessary negative energy, potentially eliminating the need for manufactured exotic matter altogether. Energy requirements present another formidable challenge. Opening even a microscopic stable wormhole would likely require energy equivalent to converting an entire stellar mass into pure energy, exceeding humanity's current annual energy production by factors exceeding 10 to the 35th power. Civilizations capable of such feats would need to harness energy at level 2 on the Kardashev scale, capturing the entire energy output of their star through massive structures like Dyson spheres. Precision engineering at quantum and relativistic scales would be necessary to shape spacetime itself. Current technology struggles to maintain quantum states against decoherence for more than a few seconds in controlled laboratory environments. Creating stable spacetime geometries would require quantum coherent manipulation at scales billions. of times more precise and extensive. Radiation shielding presents yet another obstacle. Theoretical models suggest intense Hawking radiation and other quantum effects would generate extreme radiation near the wormhole throat. Even if the structure itself could be stabilized, any matter passing through might be subjected to radiation levels millions of times beyond lethal doses. Advanced shielding technologies, perhaps based on electromagnetic fields or exotic matter configurations, would be essential for survivable transit. Navigation systems capable of targeting specific destinations within the multiverse pose, arguably, the greatest challenge. If other universes possess different fundamental constants or physical laws, conventional sensors and navigation equipment might function unpredictably or fail entirely upon arrival. Autonomous probe systems with adaptive physics models would need to precede any crewed expeditions, establishing communication relays capable of transmitting across universe boundaries. Temporal effects add further complications. Different regions, connected by wormholes, might experience different time rates due to relativistic effects. Without precise temporal synchronization technologies, explorers might return to find their home universe aged thousands or millions of years during what subjectively felt like a brief journey. Some theorists propose a more gradual approach through quantum entanglement manipulation. Rather than creating macroscopic wormholes immediately, advanced civilizations might first establish quantum communication channels between universes through entangled particles, gradually expanding these connections through accumulated quantum effects into traversable pathways. Despite these challenges, the laws of physics as currently understood don't explicitly forbid wormhole creation and stabilization. They merely set extraordinarily high technological barriers. A civilization thousands or millions of years more advanced than our own might develop approaches currently beyond our imagination, just as smartphones and space travel would appear as magic to humans from just a few centuries ago. While creating artificial wormholes presents seemingly insurmountable technological challenges, another possibility exists. Natural wormholes may already exist in our universe. Several observational efforts are underway to detect signatures of these theoretical structures, operating at the intersection of astronomy, gravitational wave detection, and quantum physics. Gravitational lensing provides one potential detection method. All massive objects bend light passing nearby, creating distinctive distortion patterns astronomers regularly use to detect dark matter and distant galaxies. A wormhole would produce unique gravitational lensing effects distinct from those created by normal matter or black holes. In 2020, researchers from the Central Astronomical Observatory in Russia proposed specific observational methods for distinguishing wormhole lensing patterns from those of conventional objects. These patterns would include characteristic double rings with specific brightness ratios. Using data from instruments like the Event Horizon Telescope, which captured the first image of a black hole in 2019, astronomers have begun searching for these distinctive signatures around unusual cosmic objects. Unusual motion of stars near the centers of galaxies might provide another telltale sign. In 2019, researchers from the University at Buffalo and Yangzhou University published theoretical work describing how stars orbiting near a wormhole mouth would follow trajectories distinguishable from those around a black hole of equivalent mass. Long-term observations of stars in galactic centers, particularly around the supermassive object at the center of our Milky Way, could potentially reveal such anomalous orbital patterns. Gravitational wave astronomy, inaugurated with the 2015 detection of merging black holes by the Laser Interferometer, Gravitational Wave Observatory, LIGO, offers perhaps our most promising approach for wormhole detection. Wormholes undergoing dynamic processes would generate gravitational wave signatures distinct from those produced by black hole or neutron star events. Theoretical work published in Physical Review D in 2021 described specific waveform characteristics that would distinguish wormhole signals from other gravitational wave sources. Another intriguing possibility involves cosmic rays, high energy, particles from space that regularly strike Earth's atmosphere. If wormholes connect our universe with others having different physical properties, Cosmic rays originating from these other universes might display energy spectra or particle compositions, violating our physical laws. Several cosmic ray observatories, including the Pierre Auger Observatory in Argentina, maintain ongoing searches for such anomalous particles. Quantum experiments provide yet another approach. Under the ER-EPR correspondence discussed earlier, patterns of quantum entanglement might reveal underlying wormhole geometries. Laboratory experiments with quantum simulators and entangled particle systems now explicitly test these theoretical connections, potentially offering insights into natural wormhole formation. Even if macroscopic wormholes remain elusive, microscopic or quantum wormholes might be more common. Theoretical work suggests that space-time itself may have a quantum foam structure at the smallest scales, with microscopic wormholes constantly forming and dissolving as part of quantum fluctuations. While individually too small and ephemeral for traversal, these quantum wormholes might be detectable through their collective effects on high-precision quantum measurements. Several astronomical anomalies have periodically sparked speculation about natural wormholes. These include regions with unexpected emissions patterns, gravitational anomalies, or objects with unusual spectroscopic properties. While conventional explanations usually emerge for these observations, astronomers maintain catalogues of unexplained phenomena that undergo continuous re-evaluation as our theoretical understanding advances. If natural wormholes do exist, they might offer significant advantages over artificial constructions. They would have already solved the stability problem, potentially through natural configurations of exotic matter or through quantum effects we don't yet understand, making them prime targets for exploration or technological enhancement by advanced civilizations. Beyond the scientific and technological questions surrounding multiverse exploration via wormholes lie profound philosophical implications that challenge our understanding of existence itself. These considerations transcend physics, touching on consciousness, identity, ethics, and the very meaning of reality. If we could someday traverse to parallel universes, what would we find? The answer depends crucially on which multiverse theory proves correct. In bubble universes arising from eternal inflation, we might encounter realms with radically different physical constants, perhaps universes where stars cannot form or where complexity never evolved. In quantum many-worlds universes, we might theoretically encounter alternate versions of ourselves whose histories diverged at crucial quantum junctures. This raises challenging questions about personal identity. If you encountered an alternate self, identical in every respect, except for a single different decision made years ago, would they be you? Would you share consciousness or merely physical similarity? Philosophers like Derek Parfit have grappled with such questions through thought experiments involving teleportation and duplication. But wormhole connections to quantum parallel universes would transform these thought experiments into potential realities. Ethical questions abound as well. Would we have moral obligations toward beings in other universes? If a civilization discovered it could divert catastrophes into parallel universes, rather than facing them in their own, would such actions be ethically defensible? The philosopher Nick Bostrom's vulnerable world hypothesis suggests that technological advancement inevitably uncovers capabilities that threaten civilization's survival. Multiverse access could either mitigate such threats through diversification or amplify them through interdimensional contagion. The nature of reality itself would face re-evaluation. Most humans throughout history have conceived of reality as singular and objective. The confirmation of accessible parallel universes would shatter this conception, requiring new ontological frameworks. Philosopher David Lewis's modal realism, which argues that all possible worlds are equally real, might transition from abstract philosophy to concrete cosmology. Religions and spiritual traditions would face profound challenges and opportunities for reinterpretation. Concepts like afterlife, divine creation, and cosmic purpose would require reconciliation with a reality of multiple universes, each with potentially different physical laws and evolutionary histories. Yet some traditions might find validation in ancient ideas about multiple worlds or realms of existence, found in various mythologies and texts. The Drake equation, which estimates the number of communicative civilizations in our galaxy, would require expansion to consider civilizations across the multiverse. Such developments would fundamentally transform the search for extraterrestrial intelligence, potentially explaining the Fermi Paradox, the apparent contradiction between high probability estimates for alien civilizations and the lack of contact. Perhaps advanced civilizations invariably discover multiverse travel, abandoning their original universes for more hospitable ones. From a purely pragmatic perspective, multiverse exploration could offer solutions to existential risks facing humanity. Climate change, asteroid impacts, supervolcano eruptions, or even the heat death of our universe would become survivable if humanity could transfer to alternative universes with different conditions or histories. The ultimate backup plan would not be another planet, but another universe entirely. Yet perhaps the most profound implication returns us to the ancient philosophical question: why is there something rather than nothing? The multiverse hypothesis offers a potential answer, that nothing is unstable, inevitably generating everything possible across infinite cosmic variations. This perspective transforms our universe from a singular precious accident into one instantiation among countless others in the grand tapestry of existence. Whether wormholes will ever serve as our gateways between these worlds remains uncertain, but the very possibility stretches our imagination and expands our conception of reality's ultimate nature. As we continue advancing our understanding of theoretical physics, we edge closer to answering whether the doorways between universes will forever remain mathematical abstractions or someday become the portals through which humanity takes its next great journey.